What's up my friends, welcome back. This will be an update video about this project here, which is the Pure Sine Inverter, because I had a lot of questions and also some warning messages on my previous video. And by the way, if you want to see that video, we'll have it I think here or in the description below. So go there and check that out. This was an amazing project. For me, it was a huge success because first of all, it works, it has a lot of power, it's a bit dangerous, and for me it was a huge success because I was a little bit worried that it won't work or maybe I will make it blow and so on. So that's why for me it was a huge success. Now, is this PCB perfect? Obviously not. It's still like a prototype, it's not like a well-engineered PCB, it's not for selling it online and so on. But it does work and it works pretty good. So in this video I want to go over all those questions and warning messages that I got on my previous video and clear all those out. So guys, that being said, let's get started. What's up my friends, welcome back. Before we even start, I want to say that this PCB has a lot of room for improvement. So I don't say that this is a perfect PCB, it's not made for commercial use, I'm not planning on selling it, it's just a prototype for me to learn how it works and also teach you how it should work. So in case that you want to make this, please be cautioned because this is not perfect. Also have in mind that this works with high voltage and it could be dangerous. So if you're not sure of what you're doing, don't start it. So for those who are commenting, I take all your critiques as a positive feedback, even if some of those messages were insulting me, literally. But anyway, now we could start with the questions. And the first question is about voltage and frequency. Okay guys, so for the first question about this Pure Sine Inverter, it was how to adjust the voltage output and the frequency, because some of you guys were saying that this is not compatible, for example, with USA, because this output is of 230 volts AC and 60 Hz for here in Spain. But for example, in USA, you have 150 AC and 50 Hz. So that's very easy to fix. You can just solder some pads here on the back. Let me just point the camera here and explain you how it works. Okay, so this is the back side of the driver, and as you can see on this corner we have some pads that are going from JP1 to JP7. And then if we take a look on the datasheet, this is the datasheet of the driver, you can see that according to this table, by marking this, by shorting these pins JP1 to JP9, you can select the frequency, you can select the 3-second soft mode, you can select a dead time if you want. So for example, just by shorting JP1, you will change the frequency to 60 Hz, and by shorting JP5, you will change the frequency to 50 Hz. So that's how easy it is to change the frequency according to your country. And then as you can see in this table, you can change a lot of other settings if you want, just by soldering a short connection to those pads here on the back. And then if you want to change the voltage, that's more than easy. As I've shown you in the video, have this potentiometer here, which is the feedback potentiometer, and just by rotating this potentiometer you can set the voltage output to any value that you want. In my case it was for 230 volts, but if you want 115, you can just change this till you reach the voltage that you want. And each time you can control that with your multimeter, and when you get to the value that you want, you leave the potentiometer there, and that will be the output voltage. So that's how you can change the voltage and the frequency according to your country. In this case, if you want for USA, it will be 150 volts AC and 50 Hz frequency. Okay, the next comment was related with the voltage input. Now my PCB, my inverter is made to work with 12 volts input, and that's because I've made the first part, which is the DC to DC converter, which creates from 12 volts, creates 380 volts DC. I've made it based on this PCB here, because I was able to buy this from AliExpress for like $15. So this is made for 12 volts. And the comment says something like, if you increase the voltage of the input to let's say 24 volts, so 2 batteries from a car, for example, in series, you'll get less current at the input. Actually, it's half the current at the input. In that way, the MOSFETs won't get too hot, and also the tracks could be even smaller, and so on. Yes, it's right. If you increase the voltage to 24 volts at the input, the power at the input will be the same, but the current will be lower, and that's a good thing to make. But for that, you probably have to change the MOSFETs. Even these MOSFETs are made to work with up to 30 volts or so. The spike from the voltage spikes from the transformer might damage those, so you might want to change the MOSFETs or the entire design. So that will be maybe for a future update. In case that I want to increase the power, maybe I'll go with 24 volts. But even so, if you go on the market, you will find a lot of inverters of only 12 volts, because a lot of people only want to just connect this inverter to a car, which usually has a 12 to 14 volts battery, and you don't want to carry around a 24 volts battery pack with two huge batteries in series. So depending on that, it will be your decision to change from 12 volts to 24 volts. But yes, it will be a good idea, because with 24 volts, the input will be with less stress, because the current value will be half of that. In this case, I think for 500 watts, which is this PCB here, it will be like 40 amps. Obviously, 20 amps is a lot better than 40 amps. Okay, and the next question, actually not a question, just like a comment or a warning, was that this design is very bad because it doesn't have a heatsink and my IGBTs will burn out. Actually, it does have a heatsink, but it's not placed yet because this is just a prototype. That's why I've placed the IGBTs here, so you could add a heatsink like this. Or actually what they usually do for a commercial inverter, they make the entire case something like this. This is just an ESC, but I don't have a case with these sizes here. They make the entire case go all around, and the MOSFETs will go just stick in place like that with some protection in between, and that will act as an heatsink. Actually, in the video when I made this PCB, I already told you that I should make or maybe buy a case like this one and place it here. Maybe I should place these IGBTs just a little bit closer to the edge of the PCB and also make something for these MOSFETs here. Now for these MOSFETs, my plan was to use a smaller heatsink, just place it like this, so they will share the heat here, and you will actually have a case, maybe something like this one, but even bigger, with a fan here and some holes on the other side, so that way the air will pass through and cool down the heatsink and take out the entire hot air. So that will be the design. And actually, instead of making the case to fit your PCB, you could just adjust the PCB size to fit one of these cases, because as you can see, for just $6, you can buy one of these cases, which can get pretty big. I mean, not exactly these ones, but I find with some $15. Actually, I found this enclosure like this one. It could go up to 120, but you could find it even bigger than this. This is made out of aluminum. You can open it here on the half size and just place the PCB inside and then screw it closed, and it will act as a heatsink. Actually, most of the inverters have this kind of case. Let me just show you a commercial inverter, and this will be a commercial inverter, and this is the case. As you can see, these screws are actually connected inside to the MOSFETs or the IGBTs with some paste that is thermal, or maybe some of those thermal pads, which I will show you in a moment, and that's how you can transfer the heat from the MOSFETs to the case. Actually, I've opened one of these ones. That's why I started making my own project, because I bought a commercial inverter for like 150 euros, and in just 2 weeks it blew up and it doesn't work anymore. That's why I started making my own inverter, and basically these pads are placed between the MOSFETs and the heatsink, so this will ensure thermal conductivity, but it won't have electricity going through from one base to the other. So that's what you should do. Actually, this is prepared for adding a heatsink here on the side. That's why I placed the IGBTs close to the edge. And yes, if you don't have an entire case, you should use a beefy heatsink like this one, which is quite big. Maybe just make some holes and then screw it in place like this, and always use plastic screws, or at least use these kind of pads to separate the backside, because as you can see, this is made out of metal and conducts electricity, and you don't want to short them in between. So basically that's what I want to do for my next update of this project. Instead of just designing my own case for heatsink to act as a heatsink, I would just buy one, because it will be a lot of effort to make my own case, maybe CNC mill it. That's a lot of effort. When for just $20, you can buy a stock case for like maybe 200 millimeters by 80 and just re-edit this PCB to fit inside that case. So that's what I will do as a heatsink. Okay, so the next question that we have about this project, is this PCB, this design has a feedback? Well, it does have a feedback for voltage, but I'm not sure if it has a feedback for frequency. Let me show you on the schematic. So actually this potentiometer here is the one that we use to regulate the voltage output, and that is connected to the feedback system. As you can see here, let me make a zoom. This is the potentiometer, and it's connected to the VFB pin, and the VFB pin is connected to the driver, and also at the same time this potentiometer is connected to the CHR pin, which is connected, as you can see, at the output choke. So we have a direct feedback of the output. If the output changes, this will inform this VFB pin, and the SPWM signal will change in order to keep the same voltage at the output. And you can actually see that in the video, because when you connect a load such as this one, which is a Dremel of like 150 or 200 watts, you can see the voltage that is changing a little bit, and it will try to keep that 230 volts using that feedback. So we have a feedback for the voltage, but for the frequency I'm not sure, because you see, when you use an inductive load, something with a coil, such as a motor, a transformer, and so on, if you add that at the output, it might change the frequency as well, because it will create some resonance and a reactive power and so on. So the frequency might go from 60 Hz to maybe 62, 63, or even less, 57, and so on. So I'm not sure if this has a feedback for frequency, but it does have a feedback for voltage. And the next question that I get about this project is about the price. So is this cheaper to make just the homemade version than just buy a commercial inverter? It might be. For that, let me just show you the inverter that I'm talking about, the inverter that I bought, which was advertised to be of 2000 watts, but it's actually not of 2000 watts. This is actually the inverter that I bought. I don't have it right now because I bought this for my uncle and it already burned out. And as you can see, it is advertised at 2200 watts and it costs like 150 euros. But actually when we connected like 500 to 600 watts, this just turned off in just 5 or 6 seconds. And that's mean that this is the peak power, not the actual power. So have in mind that this is like maybe 600 watts and costs you like 153 euros. Now let's just talk about the price of the homemade version. So let's just make just a brief calculation about the price. Have in mind that the most expensive part of this project were the PCBs, because when you make a homemade version of this, a homemade project, the lowest amount of PCBs that you can order is 5 PCBs. And as you can see, these are not 100 by 100, so we don't have the offer of $5. So this cost me $40, and that includes shipping. But if you are a company, for example, that you will make 1000 PCBs, you can get the price low to maybe down to $1 for each PCB. So it wouldn't be the most expensive part. But in this case, since I ordered 5 PCBs, including shipping, it cost me $40 for the PCBs. Okay, so on top of those $40, we have to add the rest of the components. But those are actually not that expensive. For the DC to DC converter input, I've based this PCB on this other PCB that I bought from AliExpress, and this cost you only $12 or something like that. And I literally took out the transformer and the MOSFETs and placed those on my PCB. So we have $40 the PCBs and $12 this inverter, and then you add just simple components such as this coil, which cost you like $6 or $7, the choke and the capacitors maybe $1 more, and the rest are just simple components. For example, the resistors and the small capacitors, this potentiometer. In my case, I don't have to buy those because I already have those in my workshop. But for you, it will be like maybe $1 or $2 because these are very low cost. And you might wonder if the driver is very expensive. Well, it's not. This driver will actually cost you like $3 or something like that. Or if you want the model with the LCD screen, it will cost you $4. And this LCD screen is used to show the voltage and the current and also the temperature. So maybe a total of like $4 for this one. And the IGBTs are a little bit expensive because you have to buy a pack of 10, but a pack of 10 will cost you like $20. So maybe $2 for each IGBT, which is not that expensive. So let's just say $40 the PCB, $12 this inverter, and maybe $20 for the rest of the components. So let's just say a total of maybe $80 for the PCB. And on top of that, remember that you have to add the case, the enclosure, which will be made of metal. So I found the case that will be this size for like $20, plus a small fan, which will cost you $1. So let's just say $110 for the homemade version. And you have to have in mind that this was tested with 500 watts and it works, but the other one at 600 watts will automatically shut down because it has a safety feature, and it is advertised of 2200 watts, but at 600 watts it will power off. So have that in mind. I mean, I'm not recommending you to make this for a longer use because this is just a prototype, but the homemade version would be a little bit less expensive than the commercial one. Okay, another question was related with this voltage regulator here, because this will output 15 volts, but then on the schematic I show you 12 volts as you can see here. Well, the reason that I'm using this one is because I did not have the 12 volts, but this driver, if you check the datasheet, will work with 15 volts as well, because those 15 volts will come from here, connected to those 12 volts pin, connected to the driver and also to the fan. The fan will just be connected to a MOSFET or a BJT transistor, and it will activate if the temperature is too high, so that won't have any problem with 15 volts instead of 12. And if you take a look at the schematic, I'll try to put this on the screen when I edit the video, you will see that those 12 volts pin is also connected to the VCC pin of these drivers. These are MOSFET drivers, and this can work with up to 24 volts I think, so there will be no problem to connect 15 volts instead of 12. So don't worry about this regulator, but if you want, you can use the 12 volts model instead of this one, which is the 7815 for 15 volts. And the next question was also related to the schematic, because some of you told me that the IGBT bridge doesn't have a Bootstrap implementation. Well, it actually does, and let me show that on the schematic. So you might think that this doesn't have a Bootstrap connection because you don't see it here, but if you take a zoom here, you can see that we have in the middle position, well, this is the bridge, this is the IGBT bridge, we have the high side, the low side, and then in the middle we have these VS1 and VS2 pins, which are connected to the driver. And if you take a look at the schematic of the driver once again, you will see that those VS1 and VS2 pins are connected to the feedback, to the Bootstrap connection of these MOSFET drivers. So it does have a Bootstrap connection, and basically what Bootstrap it will do, these two here on the downside are connected, always connected to the ground, but when these two are off, these don't have a reference because they will be floating, because on this pin we have nothing connected. So having the Bootstrap will make this to not have any kind of problem. So we do have a Bootstrap implementation. The next observation was about this shunt resistor, which is basically just a piece of metal with a non-resistor resistance, which is very low. In this case, the parallel of these two is of 10 milliohms. So let's just make some calculation. Let's just say that the input is of 500 watts at 12 volts. That will equal a current value of around 40 amps. So 40 amps multiplied by 10 milliohms will give us a voltage drop of like 0.4 volts. And someone commented that the voltage input of this will be saturated at 0.5 volts. So it could easily read a 0.4 voltage drop, so we don't have a saturated shunt resistor. So we basically read the voltage on the shunt resistor in order to know the current value. So if we have 40 amps passing through the shunt resistor, the voltage drop will be 0.4 volts. The driver could read that, and if the value of the current is overpassed, it will shut down the entire output is just as a safety feature. So have in mind that if you want to increase the power output by adding more these drivers at the input, you should also add more shunt resistors, because the more shunt resistors you have in parallel, the resistance will go lower. So for more current, the output voltage will be the same. So the driver will read always the same voltage. And the next comment was that I was using a bad full bridge rectifier for the high frequency part. And yes, right, this was my bad, because when I was designing this PCB, I haven't ordered a good rectifier for this purpose, and I've used just one that I had laying around, which was made for 50 Hz, which is the normal input from the outlet. And yes, this part here, which is the DC to DC converter, works at 400 kilohertz. So the rectifier that I've used is not made for high frequency, so it will generate a lot of losses. So yes, it's my bad. I will change that for the future update and place a good rectifier and good diodes that will work with high frequency to rectify the voltage of 380 volts. Okay, another comment was about the use of the solder on top of the tracks in order to increase the current pass, so it will withstand more current. So someone told that just using solder it won't work because solder is not a good conductor. Well, I prepared here a piece of copper and also a piece of solder with the exact same length, and we'll test the resistance between these two, and you will see that it's not that bad. So here I have my multimeter. Let me just measure the resistance of the copper wire. It's 63 ohms. No, 0.063 ohms. So 66 milliohms. Let's connect the solder. As you can see, the resistance is of 92 milliohms. If we compare this 92 versus 66, we get something like 30% less, 30% increase of resistance. Have in mind that the layer thickness of the copper is very thin compared with the layer of the solder, because we add a lot of solder. This is very thick. Another way to increase the current pass is to just add a wire on top of this and then just fill it with solder. So the wire will conduct the current even more. But using solder to increase the current flow is a very good technique, because you will add a lot of solder on top of these tracks to increase the power. Now yes, it will make this a lot more dangerous because you have all these exposed pads, but have in mind that this will be insulated inside of a case, and you have to make sure that none of these pads will touch the case. And that's it. That's why I've used solder on top of these tracks, because these are like 4 or 5 millimeters width, and by adding solder on top of them, you will make that can withstand a lot more current. And if you go online, you will see that the solder that I'm using is between 30 and 35 less conductive, so it's not that big of a problem because you use a lot more solder than the layer thickness of the copper. Yes, you could also order the PCBs, with the copper layer a lot thicker, but that will cost you a lot more. In my case, I made the decision to just add solder on top of the tracks. And the few questions were about the transformer that I was using, because I haven't given any reference for the transformer. Well, that's because I've used this transformer from this module, and I don't know what this transformer is because it's already assembled. But I did find one that is like this one, that is outputting 380 volts, 220 volts, and 80 volts. So it will be the exact same like this one, as you can see here on the back. Let me just show that transformer. So I found this one. As you can see, it's also 500 watts. It cost you $10, and it will have an output for 220 volts, 380 volts, and 12 volts. And it has the exact same size and connection, so I guess that this is the transformer that the module is using. Okay, the next warning was about the efficiency of this inverter, because in that video I say that it has an efficiency of around 80%, but then I also show you an example that I have an input of 60 watts and the output connected to the load, which was a light bulb, was of 40 watts. So we have a 20 watts lost, and that would result into efficiency of only 60%. But those 20 watts are even in the idle position, so when you don't have nothing connected at the output, you still have like 10 or 15 watts of power that are lost in the circuit. And I'm pretty sure that the power is lost here in the rectifier, because then when we connect the Dremel, which is a 150 watts, we have 150 watts at the output, but only 185 at the input. So we have 35 watts of lost power, and that will equal to like 20 or 20 something of power losses, so we will have an efficiency of 80%. That's why I said that this has an 80% efficiency. With the first example is not a good example because we have 20 watts that are lost, but those 20 watts also include the losses of the PCB by itself, for the rectifiers, for the voltage regulators, and so on. So this will have an 80% efficiency, more or less. Oh, and by the way, talking about efficiency and voltage input and current input, for my test I was using these wires. Don't do that, because if you use this for the total power output for 500 watts, that equals to 40 amps of current, and obviously you can't use these wires. I was using this just for the test. You should use wires that are a lot more thick than this, because 40 amps is a lot of current. So have that in mind. Never connect at the input thin wires. Use thick wires. Okay, the next question is, how can you increase the power from 500 watts to more than that? Well, you will have to change a little bit the schematic, but you have to have in mind that the power output is given by the power input, by this part here, the voltage regulation of the high voltage part, which is based on this transformer. Now, this entire part here is made for 500 watts. If you want more than that, you should add more of these modules, like this one, in series. Actually, when I've opened that 2000 watts inverter, I can show you that it has more than just one transformer. It has 3 transformers, because in that way you can get 500 watts of power at the input, and then the IGBTs and the output coil is more than capable of controlling that power. So if you want to increase the power, you should add more of this in series to increase the input power to maybe 1000 watts or even more. But have in mind that for that you should change a little bit the circuit. For example, the shunt resistor, maybe the IGBTs will need more power dissipation, or even use, instead of just 4 IGBTs, use 8 of those. So yeah, have that in mind. You could increase the power, but it's not that easy. Okay, so just to sum this up, some improvements that I want to make for this PCB, which is not perfect, are to add a fuse, because I forgot to add a fuse, and it's very important to have a fuse in case that you have a short circuit or something like that. I mean, the driver will detect the short circuit with the shunt resistor, but it's better to have a fuse. I'll add a fuse. Also, I want to add leakage resistors connected to the huge high voltage capacitors. In that way, when you disconnect power, they will slowly discharge, and it won't create any hazard, because in that way, in like maybe 10 seconds or 15 seconds, the capacitors will be empty and you can touch them. I mean, I don't recommend to touch them, but you don't have to discharge them through an external resistor, because it would already have the resistor on the PCB. Okay, so as improvements, I'll add these leakage resistors or bleeding resistors, I'm not sure how you call them, so it will discharge these huge capacitors by itself. I'll also add a fuse. I also want to change the full bridge rectifier to work with high voltage and high frequency. I also want to change the entire design so it could fit inside of a case, so we will have heat dissipators for the IGBTs and for the MOSFETs. And I'm not sure what else I could change for this to make it even better. So guys, that's it for the update of the Pure Sine Wave inverter. I hope that you like it and that now you understand a little bit more how to adjust the frequency, the voltage output, why we need all these components, why we need the shunt resistors, why we need some bleeders for the bleeder resistors for the high voltage capacitors, why we should add a fuse, why you shouldn't use this full bridge rectifier as I did and you need a high voltage, high frequency one, and so on. So I hope that this will be an update for the future version, and once this design will be ready together with a case, I'll make version 2, which I hope that it will work a lot better and it will be prepared for longer time use because it will have the heatsink, the fan, and so on. And that being said, thank you very much and see you in my next video. Keep up, you guys. So guys, here I am in my workshop, another video that ended. I hope that you like it, and the most important part, I hope that you have learned something new. Anyway, I just wanted to give a thank you to all my patrons, to you guys, to the viewers who are supporting me, liking my content, sharing it, commenting below. Just check my website, check my shop, check my t-shirts. All this kind of stuff will support my channel. So thank you very much once again.